Okay, so today is going to be our second Fixman theory lecture on kind of both simulation and analysis of protein systems. So this is day 8 of our workshop. And so first, just find out how everybody was able to do with running these simulations yesterday. Everybody got their simulations of those 3 systems to run. Were you able to visualize them in BMD, download them, part of the trajectory, at least take a look at it? Did anybody notice any big differences between the proteins that had the disulfide bonds included and the ones that didn't? Not really too much of a global difference? Okay. So, sorry, say it again? I guess you're focusing on that. Okay, so we're gonna do some stuff at the end of the day today. Part of your project will be to take those trajectories and analyze those distances in between the cysteine residues and see if you see a local difference in those proteins as a result of having or not having those disulfide bonds. So we'll make this more quantitative later on. But it's good everybody was able to get things to run, get things to work on the GPUs. So let's go ahead and get started with stuff for today. So let me screen share. Okay. All right. So in this day 8 directory, we have 2 things right now. We have 2 subdirectories, the sample trajectory directory, which basically is just a copy of the trip gauge stuff that you should have finished running yesterday. And so we have all the production runs for trip gauge here. We're going to be using this for kind of the in-class stuff that we do today. And then, like I said, for the out-of-class stuff, you're going to be looking at those trajectories that you produced yesterday. And then in the script directory, we have a handful of subdirectories, one called BMD, one called CPP Traj, MD Analysis, QuickPlot, and the project directory. The project directory will explain what your project is, and we'll get to that last. And then within each of these directories, there are, again, several subdirectories, and we'll go through each of these. There are a number of subdirectories that correspond to specific types of analyses that I'm going to talk to you about. In the BMD directory, a handful of files that we'll go through, and then in the MD analysis directory, a tutorial, a plotting script, and some sample output. And so we'll go through this tutorial in kind of some detail together. And as we go through the tutorial, what I'm going to ask you to do is to use your other terminal to start up a session of what's called interactive Python. So IPython, where you can type in the commands as you go, see what they're doing, see how they work. And then later on, you could go back and you could take that, all those commands that you wrote in the interactive console, put them into a script if you want, and then run that series of steps as a Python script instead. And so we'll talk about that. But the first thing I want to do is just a little bit of BMD. So the point today is to show you how to do some analysis of molecular dynamic simulations using a variety of tools. And that there are, many different options to perform some type of a calculation on an MD data set. That there's not just one way to do things. And in fact, sometimes, a good thing to do is to check that 2 different methods of calculating the same quantity give you the same result, right? It gives you a little more confidence that what you've calculated is, reasonable. So the first thing that we're going to do is actually we are going to go and make a combined trajectory of each of these individual pieces of the trip gauge trajectory. So if you remember yesterday, we ran 10 little segments of trip gauge, and each of those was like 50,000 steps or something like this. What we want to do now is splice them together so that we can look at them in BMD, for example. So we're going to do this, download it to BMD, and then take a look at the trajectory briefly. So go into your CPP Traj directory. And so CPP trash is a program within the Amber Tools package of programs. So it's kind of a very multifunctional analysis package for simulations. It doesn't just work on Amber trajectories. You can analyze PDB files, you can analyze DCD files, which is a format that AMD, for example, typically writes to. So it's quite robust in terms of the number of different types of file inputs and outputs that you can handle. I would say the major difference between it and something like MD analysis is it doesn't really have a built-in scripting component to it. It has a kind of set number of analysis functions that you can use in CPP trash. And so, but actually there's quite a few, and you can find all those in the Amber manual. So there's have both a part that corresponds to how to run Amber simulations, and then it has an analysis section too, which goes in great detail through things like CPP trash. Okay, so let's go into the load filter subdirectory, and let's take a look at this script. So this is a CPP trash input script, and let's take a look at it. So it was VI. And so for CPP trash, what you have to do is you have to start by reading some type of parameter file. And so for Amber force field, for Amber trajectories, this corresponds to your PRM top or your PARM7 file. And the first thing you have to do then is to read in PARM7 file, okay, to give the template by which CPP trash is going to understand the subsequent reads of the pieces of the MD trajectory. Then what I do is follow that with what's called the trash in command. So this is just a trajectory reader. So this is trajectory in. I write the path to each of those individual pieces of the trajectory. And then general syntax here is you're starting at the first frame, you are ending at the last frame. And then here, what I'm going to do is I'm actually going to take strides of 10 as I read the trajectory, okay? So I'm not going to read in every frame of every file. Why might you want to do this? Well, let's say that you want to visualize the entire trajectory over all of those files in BMD. You know, for our simulation of trip cage, we did so few steps that we could, you know, probably just splice them all together, download it, load it into BMD. It would be fine. It wouldn't cause us any memory issues or anything like that with BMD. But you can imagine if you're running a very, very long simulation, right, and you have many, many pieces, and you want to load that all into BMD, it just may not be able to handle it, right? So a good way to visualize the overall trajectory is just to, you know, take a step every 10 frames or every 100 frames or something. So you can get just an overall feel for what the kind of large scale dynamics of that system are. So we're stepping every 10 steps. If you remember, what was the MD time step that we used in our simulation of trip cage? It was, so we were writing every 1,000 frames, but what was the actual time step, the integration time step that we were using? 2 femtosecond time step, right? So we're using a 2 femtosecond time step, and then we were writing every 1,000 frames. So that means we're writing a frame every what's that? Picoseconds, right? So every 2 picoseconds. So now if I'm filtering by 10, I'm looking at a snapshot of the system every 20 picoseconds, right? So I'm looking at 20 picosecond steps once I create this. So I read all those in, and then down here, I'm going to write it now to another NC file. I'm going to call, so in order to write in CPP trash, we just call the trash out command. And then Amber understands, based on the extension that you give it, what format that file is going to be written in. So if you have the .nc extension, that's going to be the netcdf binary format, the same one that we were writing the trajectory out to. So how do we actually use this? Well, first I want to show you just briefly that there is a command line. You can do interactive CPP trash in the same way you can do interactive TLEAP. So if you just type CPP trash and hit enter, you should see something like this that comes up. We're still using version 14.25, so it's a little dated. But on the cluster now, there should be also version 16 installed. We're not going to worry about that today. Does everybody get this if they type in CPP trash? So who says no? So that probably means that you don't have something in your path. So look at your bash profiles and make sure that you have these two lines in your bash profile. Bash profile. So tilde / dot bash profile. Yep. Does everybody have those lines in it? Yes, you have bash profile. Yeah, when I did it in Discord. You also have to type BI because we're in it. And let's see. Well, you have Amber 14. You have that there. So. Okay. So actually, that's not. So is the error that everybody's getting something about G4 libraries?
I think so, yeah.
Okay. So.
Yeah.
Okay.
And GL.
Yeah. Yep. So what I want you to do then is we'll need to. So does anybody have any of these healthy library path lines in their bash profiles? Okay. So So I have a file in my directory now. Let's see, where is it? Let me just do this. Okay, in my directory called lines.txt. So copy those lines out of that file and paste them into your bash profile if you are having CPP trash errors. After you have those pasted in, you'll source your bash profile and hopefully things will work at that point.
Is there a specific place to add them?
No, just put them in there. Yep. I'm putting them down at the bottom. That's fine. Yep.
I still got it there.
It's Sunday. You have a file.
How do I get there?
Well, that's our text. Yeah. The thing that you have a file. Like, what do you look at?
Did you sort of
thing? I had open. I'll close. So source dot bash.
Yeah, yes, the source, I mean, not just dot, but you have to do, tilde / dot bash profile. You have it, Matthias, it's working out CPP trash? Ellery, you got to go. Do you need help?
Yeah, I'm still getting the error, even though I'm
Did you source it?
Oh, wait, where?
Did you source the dash profile? Yeah, source it.
That's fine.
So save.
I did it.
Okay. And then type the word source. And then type the file.
Yeah.
Yeah.
Is it the dot slash back or the tilde?
Tilde slash dot dash profile. Yep. That's that GPP here. There you go. Yep.
Alright. Thank you.
Okay. Everybody's got it working there?
Yeah.
Okay, good. So, so if you type CPP trash, let me go back into the appropriate folder. You should see this pop up again. If you type the word help, it'll give you a list of all of the different possible commands that are available in CPP trash, similar to what we did yesterday with TLEAP. And then you can, do help some particular command in here. So if we did help trashin, for example, it tells you the syntax for using trashin. So it'd be trashin file name, which is what we did, right? Then the next thing it tells you is that you give it the starting frame, then you give it the stopping frame, or you can give it the word last if you want it to go all the way to the end. You give it the that offset, so what step you're taking, and there's some other parameters, arguments you can give it as well. And then here, so some other stuff in the help information for the trashin command tells you about what the extensions are for each of the different file types and so on and so forth. So as you see, these help commands in these Amber Tools software, Amber Tools programs are, quite useful. If you ever need to know what a command's doing, you can do that. You can also look in the Amber manual. So we are not going to run CPP trash interactively in our script. So how do we run a CPP trash script? Well, we type CPP trash, and then we type -i, so it's going to be our input. And then we're going to do load and filter trash.in. And then I'm going to redirect the output to a log file because I want to keep track so I can go back later if there are errors or anything that I need to go back and double check. I want to keep track of everything that CPP trash did. And I want to give this my own log file name. It'll automatically create a file called cpptrash.log if you run it interactively. But for scripted output, you want to create a log file explicitly. So I'm going to call this load and filter trash.log. Okay, so that way I know that this corresponds to that script. I know this is the log file from CPP trash corresponding to running the script. Then I'm going to hit enter. And I'm told that there is an error because it can't find the files. So let me see if that directory is wrong. And it is. It should be 3 directory paths back. So if we go back into our input file and we just make each of these, we add one more .. slash to each of these lines. Like that, and save that, and try to run it again. You should get no complaints, and then if you type ls, you should see now that you have a file in your directory called tripcage.step20picoseconds.mc. Does everybody have that? Not quite.
Yeah.
Okay. All right. So let's go ahead and download that trajectory to our local machines now so we can look at it with VMD. So you can, of course, do that using SCP if you know how to use SCP. I'm just going to use SFTP because it's quick, but you can go ahead and do it however you want. So go ahead and copy your files. So the ones that you'll need are
What's the command? You have to run the thing.
CPP trash space -I, and then the name of the script. And then I redirect the output to a log file. So right caret, and then the name of the log file that you want. And so what we need is we need to download the trip cage, that step 20 picoseconds.nc file. And you also need the parm7 file, and that is back in the sample trash directory. So you need to also copy tripcage.parm7 to your local machine. Okay. Does everybody have those files downloaded? Okay.
Getting errors with the CPP trash thing.
What errors?
Well, it's telling me that it doesn't match the file, but I changed the. I think I just don't have the right number of slashes and dots in the lines.
It should be a .. Yeah, I tried that.
No,
slash .. is never going to work right because we said that first slash means that you're right.
Okay, so yeah, so I ran exactly. Oh, I didn't do the top line.
Yeah, top line as well. Yep.
So what are the files you use?
So you need the tripcage.parm7 and tripcage.step20 picoseconds.nc, the file that you just made using CPP trash. You have both of those?
I get it.
Okay.
Any permission to not, I'm trying to.
What do you mean trying to move?
We'll try to copy from the cluster to my local.
Are you using SCP, right? Are you trying to use SCP?
Yeah, SCP, right in the path.
Yeah, maybe it's your password.
Yeah, copy it. Like it shows like export LD library path, like put a password there, and then I accept. User path.
Mhm.
Yeah, get that.
Right, because that's what you're pasting as password, so I don't have you copy the password.
Oh.
Yeah. Yeah, try that again.
Which directory did the step 20 picoseconds file in?
That should be in the directory in which you ran CPP trash.
Okay.
Yeah. Okay, does everybody have their files downloaded? So we can go ahead and, however you open VMD, I have it aliased, you may not, but we can open VMD, we can load in the ARM7 and trajectory files. And we can take a look, for example, at what the trajectory looks like. So we can drag the slide bar, as you know, look at everything. This when VMD first loads, it's going to be in lines representation. And then if we go up to graphics and representations, And let's just choose protein. So let's type in the keyword protein. And let's put the drawing method in new cartoon. So now we should have something that looks like this. This is the trip gauge system. And if we go ahead and play this trajectory, we see that it's 50 frames of trajectory. We can slow that down a little bit. And it, of course, doesn't change conformation very much. It was already in this nice, stable, folded state. Okay, so does everybody have that running on their desktop? Good. So now we're going to do a little bit more with VMD. So I want to show you how to just do a couple of minor things with VMD. So let's go back to your script directories on the cluster. Go ahead and leave your VMD window open, and let's go into the VMD directory. And what I want you to do now is I want you to download these TCL files to your local machine. So download each of these TCL files also to your local desktop. Okay.
All the TCL files?
Yep. And so you can get them all at once by just doing star.tcl, asterisk.tcl. Download them all in one command. Yeah.
I just went to VMD. Where are the TCL files?
They're in the VMD directory, in the scripts directory, which is, yeah, within the day 8 directory.
You just do asterisks.
.tcl, yep. And then your dot for here, you know, for your, where you want to copy it to. So. Okay. Is everybody set? Good. Okay, so first let's take a look at a couple of things in the VMD menu. So VMD has this nice analysis menu, actually. I'm not sure if any of you have played with this in the workshop yet, but there are a ton of different analysis tools within VMD. You know, so for example, you can calculate hydrogen bonds using VMD. You can calculate salt bridges using VMD. You can calculate the root mean squared deviation of whatever selection of the system you would like using several different calculators within VMD. You can use a tool, there's a nice tool in VMD called Timeline, which allows you to do things, for example, like calculate the secondary structure over time for a protein. So let me just go ahead and show you an example of this. So secondary structure, like we talked about yesterday, is the presence of, you know, these alpha helices or random coil regions or beta sheets. So if I calculate secondary structure over time for my system, you see the trajectory plays in the background, and it'll give me over time for each amino acid in the system based on this color labeling scheme, what type of secondary structure I see in the system. So this is a nice way, if you have a relatively small number of frames to analyze, that you can get an idea of various trends in your trajectory very quickly using these types of timeline tools. And so another one, for example, if I want to calculate hydrogen bonds, I can give a distance cutoff and an angle cutoff for hydrogen bonds between amino acids. And here we'll see some type of timeline representation of whether there is a bond present between, and these are atom numbers. So bond present being 1, bond non-present being 0. And so we can get these type of timeline representations of our data in VMD very quickly. So this is one useful analysis tool We're not going to go into great detail in any of these, but I just kind of want to show you what is available in this package. So the types of things that you can do. Let's look at the RMSD tool because, you know, so in a simulation, of course, we see this protein, it kind of drifts around a little bit. But let's say that we want to align this trajectory so that the protein isn't drifting. And we want to calculate, for example, how the protein's structure changes with respect to, let's say, the initial frame of the trajectory. I can do that using the extensions analysis menu and go down to what's called the RMSD trajectory tool, okay? And it'll open up this window here. The selection that ends up being in the window by default is protein. So this would choose all of the protein atoms. But let's say that we just want to, in terms of the protein structure, look at the backbone alpha carbons. So to show you what I mean by that, let's go ahead and look at all of the atoms named CA. Those are these atoms right here. So you can see because each amino acid has a alpha carbon in it, those basically follow along the backbone of the protein and give you a sense of the overall structure, right? So I don't need to do this RMSD calculation for every atom in the system. So what I can do is I can make a selection for the protein and everything that's named CA. So VMD has these selection names that you can use for atoms and residue names. If you're ever wondering about a selection that you want to make in VMD, you can go over here to the Selections tab in the Graphical Representation window. And over here, you have kind of a list of all of the single word type of selections that you can make. So there's a big list of keywords here. Down here, there is another list of keywords that you can use in making your selections. There's a lot of great documentation in the VMD manual, and also similar to the Amber mailing list that I mentioned yesterday, there's a VMD mailing list, which is very useful to go and kind of see other questions that people have asked in terms of doing analysis with VMD. So, but let's go back to this RMSD trajectory tool. So I have protein and name CA. The first thing I'm going to do is click align. And what this is going to do is it's going to do a RMSD best fit alignment of every frame, okay, in that trajectory to whatever I've chosen as the reference frame. And right now I'm saying that my reference frame is going to be frame 0, okay, which is the very first frame. So if I click align, doesn't look like anything happened. But now if I drag the trajectory bar, well, you see it doesn't wiggle all over the place. So I've taken every trajectory snapshot, and I have, or VMD has aligned this onto the initial snapshot. I can then calculate the root mean squared deviation of the carbon alpha carbon coordinates over time. I can get some statistics about what the min, what the max, what the standard deviation, what the average RMSD is. And if I go up here to File, I can plot the data and take a look at how the RMSD fluctuates over time. And so this is a quick way to look at the RMSD of some filtered trajectory that you've downloaded to do things like gauge how far away from the initial structure your trajectory has drifted over time, for example. You can also save the data. So let's say if you wanted to save the data and manipulate it later, you can go to Save Data. And then I could save this to a file. And then if you were to edit that file, you would see that it's 2 columns of data, one with the time step and one with the RMSD values. And then you could plot that with some other software. You could use it for whatever else you're interested in using it for. Okay, so this is one tool again that is frequently useful to use for kind of a quick look at trajectories in VMD. And like I mentioned, so we also have these other tools here to calculate things like hydrogen bonds between different selections of the protein. So you can pick different regions of a protein and find hydrogen bonds between one piece of a protein, another region of protein, between a protein and some ligand. Whatever selections you want to come up with. Gives you some parameters that you can play with, what the donor acceptor distance is for the hydrogen bonds, what the angle cutoff is for the hydrogen bond from linear. So you can play with that. And then again, another one that frequently used is the salt bridge analysis. That's looking for salt bridging interactions between positively and negatively charged side chains, so amino acid side chains within the protein. Very similar in spirit to the hydrogen bond calculator. You're looking for interactions now between various amino acids in the system, for example. Okay, so those are a few things that you can do with VMD just from this extensions menu, but VMD also has some scripting that you can do with it, and that was the point of downloading these scripts. So what I want to show you now is what's called, just briefly, the TK console. So if you open up the TK console, that's under extensions, TK console. This is basically a scripting console that we can use to make atom selections, to use a number of commands, for example, measuring centers of mass of various coordinates. You can do reading and writing of data files by scripting things in the TK console. So there's quite a bit of power in this scripting environment using a number of built-in functions that are available within VMD. So let's take a look at some of these scripts. Let's take a look at this script called simple.tcl. So if we look at this, what simple.tcl is going to do is it's going to write basically using the puts command. This is a VMD script. It's going to load your trajectory, and then it's going to basically make a selection for the alpha carbons in the protein, and then tell you how many alpha carbons there are in the system. So let's go ahead and do this. So let's go back over to VMD first, and let's delete this molecule. So if you right-click on it and go down to delete molecule, let's just get rid of it. So now that molecule is gone. So I just deleted the molecule that I had already loaded. Everybody got that? And now if you go to your TK console, so type ls, you'll see that you're in the right directory. And now if you just source .tcl script, let's see what happens. So if you type source, simple.tcl, hit enter, and I'm in the wrong directory. So I need to delete these .. slashes here in my script. There we go. Let's save that. And now if you make that edit and type source, what you'll see happen is it prints to the screen. This is a VMD script. If you look at your trajectory window, your trajectory is going to be back because you will have used that script to actually load the trajectory into VMD. And then if you look at the last line on the TK console, you see that it's telling you the number of alpha carbons is indeed 20. And as we said yesterday, trip cage has 20 amino acids in it. Each amino acid has 1 alpha carbon. So in fact, there are 20 alpha carbons within trip cage. Does everybody get that to work?
So you just deleted all the .. slashes?
Yep, right, because those files are in the same directory as which I'm running the script. So yeah, they're not in any other, they're not farther away.
Just with source, simple.tcl.
Yep.
Oh, I got them.
Does everybody get that to work? Okay.
Getting an error that says the command clicks is not found.
Are you typing it in the TK console?
Can you use source?
Yep. Okay.
If we're editing something on, like if I BI in the TK console, how do I save it? There's no like.
I don't know because I don't typically do that. So yeah. Okay. So yeah, so anyway, so this is an example of the very basic TCL script that gives VMD some instructions. So this line, what is it doing? It's telling it to make a new molecule, and that new molecule is going to have this parameter file that is going to have other stuff loaded into it. Then into that molecule, we are adding the file tripcage.step20picoseconds.nc. This wait for all means wait until everything has been loaded before you display it on the screen. Okay. And so basically these two lines, right, are what you would typically do from here. You would go and you would do new molecule, you would choose the parm7 file, you would load it, then you would load the other thing into the trajectory into that parm7 file. So you can script that as well. You can just do that directly from the TK console, which can be useful if you want to process a lot of data, right, in a lot of different files using BMD. You could script this up and load files, delete them, load files, delete them, and analyze them on the fly. This next line here, this is what's called an atom selection in BMD. So here we are setting a variable. So this would be like equivalent to your variable equals something syntax in Python. So we're telling it to set the variable S1 equal to whatever this selection is. So this is a BMD command atom select. And what we're doing is we're telling it to select from the top molecule. What do we mean by the top molecule? Well, if you had multiple molecules loaded into BMD, there's this T over here, which means that is currently the top molecule. So the one that these commands are going to refer to if you give them the word top. So this is currently top molecule. If you had multiple molecules, you could double click and change which one is the top molecule by just clicking in this column. And then what is the selection we're asking for? Well, we're asking for the selection everything named Ca. So everything that has the atom name Ca, which are the alpha carbons in the naming syntax that we use. The next thing we're doing is we're setting another variable called num atoms, and we're saying basically to get the number of atoms in that selection S1 that we just created. Okay, and so there's a built-in command which is just num, which you can use to do this, and so we're just saying $S1 num. That then is equal to 20, and then finally we're using another puts command which prints number of alpha carbon atoms is, and then we refer to that variable now num atoms, which we set in this line, and that is what prints 20 to the screen. Okay. Any questions about that? So these atom selection syntaxes are really important to learn in BMD, not just for scripting, but also this syntax that you would put in the script is the same syntax you would put into your graphical representation window to view that part of the system, right? So what you can do is you can test a selection in the graphical representation window to make sure that you're getting what you think you want to be getting, and then you can script that selection up into a script to do analysis on it or whatever else you want to do. Okay, so that's that simple.ccl script. Let's look at the com calc noproc.tcl script. So the contents of this script now, so the first thing we're doing is we're setting a selection, a variable called cell1, and we're setting it equal to the string named Ca. Okay. The next thing we're doing is we're making an atom selection. So what do you think is going to happen after this line? What atoms are going to be in the variable S1? The alpha carbons, right? Same thing that we just did. It's just I've added an extra layer to it, which is first I'm defining some variable which is the string that's then going to go in here instead of just typing name Ca directly, right? And so now I could use this S1 in different ways by just changing this line. Okay. The next thing I'm going to do is I'm going to figure out what the total number of frames that I loaded into the simulation was. And I can do this by using what's called the molinfo command. So molinfo command, I'm saying get me information about the top molecule, and the information I want to get is the number of frames that were loaded into that molecule. So if you just went over to the TK console, and if I type that, so let's do molinfo top get num frames, it tells me 50, right? And that's exactly right. If I look at the number of frames I loaded, it was 50. If I just type molinfo by itself, it tells me a little bit about the different things that I can do with molinfo command. So I can, for example, list all the different molecules. I can figure out the number of loaded molecules, so on and so forth. So it tells you a little bit about the usage. Okay, so why do I do that? Because now, in the same way that you were writing for loops when you were doing MD analysis, you can also do a for loop, for example, in TCL scripting in VMD. The syntax is a little bit different, but it's exactly the same thing, right? You're iterating over some variable and doing something a number of times within the for loop. So the way that this syntax goes is you initiate your for loop, set some iterated variable, for example, equal to 0 at the beginning, and then I'm going to keep going while the value of I is less than the value of n frames, okay? So this will get me all 50 frames, right? Because I'm starting at 0, and if I'm less than 50, then I go from 0 to 49, which is 50 iterations. And each time I'm telling it to increment I, and if I just put increment I, it'll know to just increment it by 1 each time through the loop. Now, what I do after that is I say, let's have that selection name $I. So I'm going to have that selection that I made up here now correspond to the ith frame. I'm going to update it. This isn't really necessary here, but if you have distance-dependent selections, you actually need to have an update command in here. Let's say if you wanted all carbon alphas within 3 angstroms of something else in the system, each frame that could change, right? Which carbon alphas are within 3 angstroms of some other group of atoms. So you have to update that frame. And then what I'm going to do is I'm going to measure the center of mass of the system. And so VMD also has some built-in measure commands. If I go over to the TK console, for example, and I type the word measure, here are all the different commands that I can use in VMD that allow me to measure things. So I can measure, for example, average positions, centers. I can do some clustering in VMD. I can measure hydrogen bonds. I can measure radius of gyration, RMSD, root mean square fluctuations. So there's a whole bunch of commands that are built into VMD that I can readily use with this measure syntax. What I'm doing here is I'm measuring the center of my selection, and the weight that I'm going to use to make that center, the measurement of the center, is I'm going to use the mass as the weights. So technically it's a center of mass. Now, because all of the alpha carbons have the same mass, does this matter that I'm telling it the weight by mass? No, right. If I had like a group of atoms that had different masses, right, then it would matter, the mass weighting, right? But when everything in your selection is the same mass, the center mass is going to be the same as the center geometry, right? So you just do measure center. We'll leave this in here anyways, even though it doesn't matter for our particular selection. And then what it's going to do is it's going to print out the frame and the value of the center of mass of those atoms in that frame. So let's go ahead and see if this works. So if we go back over here to our console and we type source, com underscore calc underscore noproc.tcl and hit enter, you'll see a list of numbers. And so what it does is it gives you the frame, and then it gives you the x, y, and z coordinates of the center of mass of that selection in each frame over the trajectory. Okay. Any questions about that? I'm going to plug my computer in before it dies. Okay, so let's go ahead and build on the kind of complexity of the script just a tiny bit now. So go ahead and you can go ahead and quit here. And now let's look at the next one, which is com underscore calc underscore proc.tcl. And what I've done here now is I have defined a procedure. And I'll show you what this means once we source this into VMD. But basically, this is now going to become, after we source this script, a command that I can call at the TK console. So it's going to load this command as now, the same way that I type measure center at the TK console, the same way I make atom select. This is a command that will be available to me during that particular VMD session. Okay. And the way that the syntax works is inside of this first set of curly brackets, I give some names of arguments that this command is going to get. So comcalc is going to have some argument called cell1. And then inside this curly bracket down to this curly bracket, this is the function that I'm writing, the procedure that I'm writing. And you can see that all I've done is I've taken what was in the previous script, and I've just pasted it in between those two curly brackets, okay? So there's nothing different in this script from the previous one. So let's go ahead and take a look at this. Let's go back over to the TK console and source com_calc_proc.tcl. If I hit enter, it's not going to say anything at the screen right now. Okay. But now let me do this. Let me type in com_calc and hit enter. And it's going to complain to me wrong number of arguments. Should be com_calc cell1. So it's telling me that I need to have some argument here called cell1. I wrote the script so I know what that means. That means I need to make an atom selection. So let me try that. So now I can type in com_calc, and in quotes, let me just type name CA. And look at that, it's the same list that we got from the other script. But now what I've given myself the flexibility to do is, instead of going outside of VMD and writing a new script to calculate the center of mass of a new selection, I can just use that command again, and I can change what I want to calculate the center mass for, right? So I can do like CA, and let's say also the beta carbons. And so I hit enter, and I get a different list. Let's say if I want to look at oxygen atoms in the system. So now I type name O, and I get this list here. Let's say I want to look at a particular residue in the system. So if I want to know the center mass of res ID number 1, I can use that as my selection, res ID number 1, and get the center mass of that. So this gives you a lot of power in terms of being able to call this function over and over and over again for multiple purposes, right, without writing the script over and over and over again. Okay, so that's great. But now we have a list of numbers in the TK console, and if I want to do something else with it, if I want to analyze it in some other way, it's not so convenient, right? I mean, I could cut and paste it into a data file, blah, blah, blah. But is there something we can do to actually get VMD to write that information to a file? So let's look at this last TCL file, which is com_calc_proc_wout, which means with output, and take a look at this. So now what I've done is I've defined a new procedure called com_calc_wout. I've given it a second argument, so I'm still giving it the selection. But now I'm giving it a second argument, which is going to be the name of an output file. Okay. And then what I do, the same way that you were doing this with MD analysis again with Python, I have to open up a output stream for my file. So I have this set O stream. This is just the name of a variable. I can name it whatever I want. And what's going to happen is that variable is going to basically refer to this file. So I'm going to open whatever the name of O file is. And this W in quotes means I'm opening it for writing. So I'm opening this file so that it can be written to. Okay. And then I have all the same stuff again, except in this puts line. This puts line ends up looking a little bit different. Now instead of just puts $I $S1COM, I'm saying put that information into that output file stream, which is going to go into the name of the out file, right, with the out file that they've created. So I have puts $O stream, $I $S1COM, and then finally I'm going to close that file at the end when I'm done iterating through my loop, and then I close my procedure. Okay. Any questions about what's going on in the script? Okay. So let's go ahead and source this. So if you go back over to your TK console, and now I'm going to source com_calc wout.tcl. So source that. Now I should have a command available, calc wout. Let me make my name CA selection. So I'm going to do name CA. And then I'm going to just type a file name. Let me call it CA positions .bat. And let me hit enter. nothing happens on the screen. But if you go back to your terminal and type ls, you'll now see you have a file called ca_positions.dat in that directory. If you look at that with VI, what's in it? The frame number and the X, Y, and Z coordinates of the center of mass. So it's very straightforward in VMD to be able to write output that you calculate using all these built-in functions to an output file. Then you could load this in somewhere else. You could do some other analysis on it. You could calculate averages. You could calculate standard deviations. You could plot this, right? You could load this into your favorite plotting software and take a look at what this looks like. So there's a whole ton of manipulation you can do. You know, so VMD has a lot of built-in functionality that ends up being, you know, quite useful for some kind of quick and dirty calculations to just kind of see what's going on in the simulation. Okay, any questions about any of that? So that's more or less what I want to show is VMD, just the fact that, you know, you do have a lot of built-in kind of graphical, you know, analysis tools built in. You can also do scripting in the TK console when it is convenient. And, you know, like I said, there is a ton of stuff you can do in here. And one of the best places to go to kind of figure out, you know, the types of things you can do and how to do them kind of efficiently is the VMD online mailing list. On the VMD website, there's also what's called the VMD script library. So you can see a lot of examples of TCL scripts that other folks have uploaded to the script library. And that's one of the best ways to learn how to do this TCL scripting in VMD is just to get examples of what other people have done and figure out how they work. Try to break them, figure out why they break. If you figure out why they break, you can figure out why they work, right? Anyways, let's go ahead and move on then. So let's close our VMD session and go back to our Colorado State accounts and get out of the VMD directory for now. Okay. So the plan was to go through both some CPP trash analysis and some MD analysis. I think in the sake of time, what I'd like to do is focus on MD analysis since that's been the common that has been the common theme throughout the couple of weeks. The point of also doing the CPP trash analysis was to show that there are a number of built-in functions within CPP trash that can calculate quantities like the RMSD, like hydrogen bonds, like interaction energies in between regions of a protein, between a protein and a ligand, in a very efficient way, and that it's you know, another way that you can compare to other methods that you write yourself or other methods from other analysis softwares that you use. So as part of the kind of homework assignment, that'll be to go through the rest of the CPP trash directories and understand and get to work the various scripts in each of these directories. And I think in each of these directories, I also have, actually I don't have sample output, but I do have the input files for each of those. So you should take a look at each of those directories. You should cross-reference them to the Amber Tools manual and figure out what you're doing, what each of these different functions are calculating. So I'll leave that part to you as a homework assignment. But for now, what I want to do is go on to our MD analysis tutorial. So let me see. I want to log into a different window here. So let me do this. Okay. So what we're going to go through as much as we can is this day8.tutorial file. Okay. And so this tutorial is basically following very closely an online MD analysis tutorial. And so I also, it doesn't do everything in the online tutorial. There's a couple of embellishments that I've added as well in various places. But I would strongly urge that you make an attempt to go through the rest of the MD analysis tutorial online and really get familiar with how to use this set of analysis tools. they're quite powerful. Gives you kind of the power of numerical Python scripting embedded in this molecular dynamics analysis tool set that allows you to load in and manipulate trajectories. Okay, so what I want you to do in your other terminal, so the one that does not have this day tutorial open, is I want you, within your MD analysis directory, to just type the word IPython and hit enter. And hopefully this works for everybody. Anybody not working? Everybody's good? Okay, great. So IPython, so this is an interactive Python session. And so you've been doing a lot of Python scripting. IPython is a nice addition onto Python. So how do you do it? If you install your own version of Python, you get this nice installer that comes along with it called pip. And you would just install Python, and then you should be able to type pip install IPython, and it'll grab IPython from some server and install it for you. So these Python packages are very easy to install. But what interactive Python allows you to do is it allows you to do some autocomplete type functions, which are very useful. So if I hit D and I hit tab, it'll show me, for example, all the commands available currently that start with D. And so this autocomplete feature can kind of help you figure out, what potential functions are available. It also has a history. So if I do like 2 + 2, 3 + 3, 4 + 4, if I want to do one of those again, I can just hit the up arrow and cycle back through my previous commands. In fact, I can even cycle back through previous commands from previous runs of IPython, so it keeps quite an extensive history of what I've done previously. This is very useful to go back. Let's say, for example, you have a series of commands that you figure out works very well, now you want to script it up. Well, you just cycle back through your IPython commands and then transfer those over into a script. Okay, yeah, Matthias. You have to hit D and then tab. So just like at a Unix terminal, tab will do autocomplete, right? Yep. Okay, so let's go ahead and get started with what we're going to work on today, though. So the first thing we're going to do is we're going to import arrays. So basically, the way I've tried to lay out this tutorial here is everything with a single hash in front of it is a command that we're going to write in our interactive Python session. Everything with the 2 pound signs is just a comment that I've made. So let's go ahead and type some of this stuff. So let's do import numpy as np. Now you should have imported your numeric Python libraries. As np means that if I type np dot, let's go to display them all. These are all the functions that belong to that stuff that I just loaded. So any numeric Python function starts with np, and then see there's things like non-zero, numeric array, ones. So we have over 500 commands imported for the NumPy library. Now, next I'm going to import is I'm going to import MD analysis. So, and you've already done this with Elijah. So if I just type in import MD analysis, enter, Rebecca.
When I do import NumPy, it says import error liquid lib quadmat soap.0.
So none of you can import NumPy? You what? You were okay. Okay, it's probably something else missing from your paths, so let's take a look. Should you do what, sir? Let me check out mine first. Yeah, so you probably need this line here. So let me go ahead and I'll make a new. Okay, so if you go into my MD analysis directory, so under my day 8 scripts MD analysis directory, I now have a file in there called lines.txt. So copy this line into your bash profile, and then save that and then source it. Ellery, you already have that line. Okay. Are you sure it's typed correctly?
Yeah.
Okay.
Yeah, it looks good.
Okay. Well, let's see. What else in here?
You have authority to do pip stuff on the cluster? Do you think if they did like all on 5?
I mean, it should be. I mean, if it works for some of us, it should hopefully work for. Yeah. I don't think that we each individually have authority. I think Martin and the sysadmin have authority. So,
If you do wage
uh, is that what you get? Yeah. So how many people actually have it working? Okay, so can we pair up in groups of 2 for now and work together on it, and then we'll try to get it fixed later on. So does that work? Okay. Okay, is everybody set? All right. So so let's go back to this file. So we should be able to import NumPy, import MD analysis. Later on, when you're going through the tutorials, you can also do this import MD analysis.tests. That is a basically a bunch of kind of benchmark tests and tutorial trajectories that you can use to follow along the tutorials on your own time. So we're not going to do that part of it right now. We're actually going to use our trip cage trajectory to do stuff for now. So the first thing we're going to do is we're going to load a trajectory into MD analysis. So, and we're going to load just a piece of our trip cage directory. So let's find that. So that's 2 directories back in sample trash. So what I'm going to do is I'm going to define a variable called parm, which is going to be sample trash, and then the trip cage.parm7 file. So like that. I define that variable, and then I'm going to define a trajectory. And for the trajectory, I'm just going to take one little piece of my trajectory. So let's do prod.1.nc, for example, and define that as trash. And so now if I were to type those variable names again, it should just tell me what the string that I've stored into those variables are. Okay. So the next thing that we're going to do is we're actually going to use MD analysis to load this trajectory into a variable called u. So u, I'm going to set this equal to MD analysis and use this universe call. And I'm going to say that I'm going to give it the parm file and the trash file. So those variables that I just defined, and I'm going to hit enter. And now I should have loaded that parameter file and that trajectory into this variable u. Okay. Any questions about that?
You hold up for just 1 second.
Yep.
I got the first 2 parts, okay, I was able to define farm trash, but when I tried to do the universe thing, it didn't work.
Did you type capital U?
No.
Type capital U.
Oh, for university, I did.
You did, okay.
Yeah. MD analysis.
So what do you mean by didn't work? What was the error?
Value error, and I just think about stuff. Like all this. And, can't load the topology file. The prod.1.
Right, prod.1 is not the topology file. So you probably defined the topology, the parameter, and the trajectory strings incorrectly. You're good?
Oh.
So yeah, be careful with what you type in there. It has to actually be the trajectory file. You got it?
Yeah.
Okay.
I read what you were doing wrong, but I did.
Okay. So I'm letting Martin know about this in case he has a chance to take a look. Okay. So we have the trajectory loaded. If you then, okay, were to type print U, so let's do this. Print U. It tells us that what we have loaded into that variable is a universe with 5,771 atoms. You could, of course, see if that's the right number of atoms by going into your parm7 file and looking at that number that I showed you yesterday, the first number in that table of numbers, and see that that matches to make sure that it's actually loaded everything you expect it to load. 5771 is, in fact, the number of atoms. We can also look at some atom attributes. And so, for example, we can look at print u.atoms, okay? And what it says is we have an atom group now with 5,771 atoms. And so these atom groups know, for example, about the residues that those atoms in the system belong to. So the amino acids that they actually belong to. If you want to know what all of the things you can do with U are, you can hit u.tab and it'll show you all of these possibilities that you could use as attributes of U. So let's try the next command in the tutorial, which is to make a list of all of the atoms in residue 5. Okay. And so if I do list u.atoms residue 5 and hit enter, what it tells me is that in sorry, this is not residue 5, this is atoms 0 through 5. So atoms 0 through 5 in the universe variable are going to be these first 5 atoms of the first amino acid. So asparagine amino acid. Okay, so that's how I can get a list of atoms. If I want to find the residue group now corresponding to certain atoms, what I can do is u.atoms :5.residues, and it'll give me a little complaint. We don't worry about this one. This is just a printing complaint. It'll actually stop the second time. And it says that within those that first group of atoms, the only residue that it finds is ASN. Okay. If I were to increase that to, let's say, 50, for example, within the first 50 atoms, I see 3 different residues. So I see an asparagine, a leucine, and a tyrosine, and those have residue numbers 1, 2, and 3. Okay, let me check something really quick.
I think I got it.
Let's see. You all have these export LD library paths in your batch profiles, right?
Yeah, I think I ended up getting it.
You ended up getting it to work?
Yeah.
Okay, what was the difference?
I don't know.
Okay.
I tried it a couple more times. I got a couple errors, and then one time I didn't get the error.
Okay. So some of you other folks may want to try that again as well to see if you can get that to work. Okay. So let's go back to our tutorial. We can also get segments, and so if I type in u.atoms.segments, for example, it tells me that the one segment in my universe is currently called system. If you had multiple segments in your trajectory, then they would be referred to as different segment names. Let's go ahead and go on and look at some other things that we can do with MD analysis. So I can define a variable, for example, as u.atoms, and let's go from atoms 10 to 50 and residues, right? So we already used this command earlier to look at which residues were within, which residues corresponded to a certain list of atoms. So now I'm saying that I want to set a variable equal to whichever residues correspond to atoms 10 to 50 in my file. So if I hit enter, I've done that. If I type R then, well, that R variable now has stored in it the first residue, asparagine, the second residue, leucine, and the third residue, tyrosine. Okay, so I've just set a variable equal to this stuff that I previously did up here. I can also see then how many atoms are in that group, for example, by now taking this variable and just typing r.atoms. So it tells me it's an atom group with 56 atoms in it, and I can list those atoms using the list command, and I can see, for example, what all of the atoms in that that I've stored into that variable indeed are. Yeah.
So if you define R to be the selection of atoms from 10 to 50, does it have 56 atoms?
So take a look at this next note. Test, right? So what you're actually doing is you're printing all the atoms that belong to all of the residues that were covered between 10 and 50, not just the atoms. Exactly, right. So you're actually, yeah, you're finding, what you're saying is find all the residues that correspond to those atoms, but what it's storing is, right, exactly, the total number. Yep. Right, so that's actually a little caveat of how this command works, right? So, but that's good that you notice that there's some discrepancy there, and then go back and figure out what the command's actually doing. Okay, so we can also do kind of these VMD-like selections within MD analysis. So let's take a look at some of this. And so, for example, I can go ahead and make some variable, let's call it CA for alpha carbons. And I can use what's called the select atom attribute. So I'm going to go u.selectatoms, and then in this kind of common syntax, I'm going to write protein and name CA, which is really the exact same thing that I would be writing in VMD. The MD analysis atom selection syntax is not quite as robust as VMD's, but you can still do quite a bit with it. And so if we type in protein and name CA, define that. If I type CA, then it tells me that I have an atom group now that I've created with 20 atoms. That makes sense because we're using the trip cage system. The trip cage system, like we've been saying, had 20 amino acids in it. Each one contributes an alpha carbon. I can also do calculations with this. So I can, for example, if I hit CA and I hit tab, there's a whole bunch of things that I can now ask about that group of atoms. So I can ask, for example, what the radii are. I can ask, what the center of mass is. I can figure out what their coordinates are. So there's a whole bunch of different options that I have. Let's take a look at total mass first. So if I do total mass, and again, this deprecation warning, don't worry about this. This just has something to do with, I believe, an older version of the total mass function. So we'll go ahead and do what they say here. But if I use total mass, I get 240.19, blah, 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 repeating. And in fact, if you were to grab the mass of carbon from the periodic table and multiply by 20, you would find that this works out. So let's actually try what they're saying here. They're saying to use this total underscore mass function instead. Okay, and so that is, I guess, the new syntax. The older one is going to probably get removed from a future release of MD analysis at some point. But anyway, so you can calculate total mass. You can calculate total charge. So let's do total charge. And that tells you the total lump charge on all of those alpha carbons. And so what are some other things we can do? Well, we can make selections based on those selections. So I can define now, let's say if I just want the acidic amino acids. So I can say acidic is equal to Ca, and then I can make a selection of atoms from that Ca selection that I've already made, right? And the atoms that I'm going to choose are the ones that are either the aspartic acids or the glutamic acids. So I'm going to make a selection for res name asp or res name glu, hit enter, and now if I go ahead and type the word acidic, that tells me there's only one atom in there that is satisfied by. And so if I want to figure out which residue that actually is, I can do acidic.residues, an aspartic acid, and its residue number is 9. And so if you were to look at the trip cage structure, you would see that this is indeed the case. There's an aspartic acid there, it's number 9. That's the only amino acid that is either asp or glu in the trip cage structure. Okay, and so you can basically, in the docs online, there are a ton of selection keywords. And so I'd recommend kind of looking through those documentation pages in order to figure out what, you know, the other type of atom selections that you can make are. Any questions about that so far? Okay, so you can also do dependent selections. So let's try this. Let's try to select atoms that are going to be anything that is a protein atom and within 4 angstroms of that aspartic acid. So we want to find everything that's within 4 angstroms of the aspartic acid. So if I type u.select atoms, so remember U is the container that has everything in it, right? So u.select atoms, protein, and around 4.0, res name ASP. Hit enter. That tells me that atom group has 39 atoms. And so then if I actually want to figure out what atoms those are, I can go ahead and put the list command around it. So I can go like this, hit enter, and I can get a list of all those atoms that are within 4 angstroms of the aspartic acid. Okay, any questions about that? So now, you know, that's fine. Should we believe it? That's another question, right? We should always check and make sure that we're getting what we want. So let's go ahead and define a variable called mySelect, and I'm going to set that equal to that selection, okay? So what I'm going to do is I'm going to go mySelect is equal to that stuff, okay? Define that. Now what I can do is I can actually write a PDB file that contains that selection. And then I can look at the PDB file in VMD to make sure that I am indeed getting what I think I want. So to do that, now that I've defined this mySelect variable, I can do mySelect.write, and I'm just going to call this mySelect.pdb and hit enter. And now if I type ls, I should see I have a file called mySelect.pdb in my directory. Go ahead and download that file to your local machine. And then once you have it, go ahead and open it up with VMD, and let's take a look at it. Yeah. So mySelect is just equal to that selection that you made a couple of lines above. Okay, let me know once everybody has their VMD file open. Everybody good? Okay, so let's go to our graphics and representation window. And let's just type in res name ASP. Okay, and so we don't see the ASP itself. Okay, so you know, we can't really decide based on this PDB file whether or not the things that we've found are actually the things within 4 angstroms of ASP. So let's go back to MD analysis and let's make a new selection. So the selection that I want you to make is now this my select 2, which is u.select atoms. And now you're going to make a selection which is the same as the one we previously made, protein and around 4 of res name asp. But you're going to put that in parentheses and then also have or res name asp, right? We have to use or and not and because this is the logical and, right? So you can't have, they would conflict with one another, right? If you had protein and 4 name asp and res name asp, you wouldn't get anything, right? Because nothing belongs, there's no atom that belongs to both those groups simultaneously. But or says that we want that first piece that we downloaded, or also res name asp itself. So what you can do here is you can do or res name asp. Okay, so go ahead and define that, and make sure that your quotes are all in the right place and your parentheses are all in the right place. And it's probably better if I just cut and paste this. So you have your my select 2. Let's go ahead and write that. So my select 2 dot write my select 2 dot pdb. Now we should have another PDB file. Go ahead and download this one to your local machine. Does everybody have that downloaded okay?
I'm not able to get it from the IPython like path bar. Like I'm trying to like SCP it, and it's just not getting to that file. Like I'm trying. I wrote the PWD, and like instead of like home, it starts with like U apostrophe and things like that.
Yeah. So don't use the U apostrophe.
Don't have the U apostrophe.
No. I mean, you just want the path. That's not part of the path.
When a PWD that's what's showed up.
Yeah, sure. But that's just some extra syntax that it's including there.
That's not what MNT.
Yep. Slash. Okay. Everybody have this on their VMD screen now? So now if I go into graphics, representations, and I type in res name asp, I get the aspartic acid this time. Okay. So I have the aspartic acid. And now let's go ahead and see everything else within 4 angstroms of that aspartic acid. So if I look at, for example, all and within, let's say, 2 of res name asp, okay? So like that. Let's go ahead and color this. Like that. And let me do one other thing here. Okay, so the yellow part is the aspartic acid, and the blue part is everything that's within 2 angstroms of the aspartic acid. So I asked for 4 angstroms on Python, right? So let's look at 3. Let's change this 2 to a 3. We get a handful more atoms. Let's change this to 3.5. I get a handful more atoms. Let's change this to 4. I get a few more atoms still, right? Let's change this to 4.1. I don't get any additional atoms that time, right? So the gives me some kind of visual confirmation that the selection that I made with Python with MD analysis gave me what I expected to get in this output file, right? I'm seeing the atoms that are within 4 angstroms of this aspartic acid residue, which is here in yellow. Okay, so why do you want to do this type of check? Well, let's say that what you're attempting to do is you're attempting to select those atoms, because what you want to do is you want to do some particular calculation in between the aspartic acid and the atoms that are within 4 angstroms of it. Well, if you just write some random selection in your Python script and you run it and you never check it, maybe your selection is not what you expected for some reason, right? You made a syntax error. So it's always good to at least download one snapshot, right? And at least see that you're getting what you think you should be getting for that selection that you've made before you go on to do some, quantitative analysis using those selections that you've made. Okay, good. So let's go ahead and go back to our IPython window. So like I mentioned here, that you have a whole ton of quantities. Basically, you can calculate for atom groups that are built in to MD analysis directly. And you can also create your own kind of routines and scripts within MD analysis too, because you have all the NumPy and SciPy libraries that are available to you. So let's go ahead and make another selection now for carbon alpha atoms. So let's define a CA variable again as u.select atoms, protein, and name CA. Okay, so we have all of our carbon alpha atoms. We can check that atom group with 20 atoms. That makes sense, right? We should be able to type, I think, ca.residues, and that'll give me the residue list. And all 20 of the residues are there because each residue has a carbon alpha atom in it. Okay, so all that checks out. Now let's go ahead and make another variable called R, and within R, let's go ahead and store the positions of the carbon alpha atoms. Okay, so if I type R is equal to ca.positions, I don't see anything I put to the screen currently. If I hit R.shape, this tells me that I now have an array which is 20 by 3, right? That makes sense. I have 20 carbon alpha atoms, and their coordinates are going to include both their x, y, and z coordinates, right, for each of those atoms. So what this should store, if I type R, is this. These are the coordinates of each of those carbon alpha atoms, right? And ultimately, when we're doing calculations, right, I mean, the reason we run a trajectory in molecular dynamics is because we want those positions. And from those positions, we can go back and calculate other quantities, right? We can throw them back into the potential along with the other parameters, and we can calculate energies and interaction energies. We can figure out, what the center of mass of some object is, what the distance in between objects is, what the angle formed between two vectors are, so on and so forth. So there's a lot of calculations that we can do if we have access to the positions. MD analysis has this very straightforward way where we can access the positions of all of the coordinates that we have read in for that trajectory. Okay, so we already saw some of these functions, but let's look at a few of them again. So we do center of mass, for example. We can calculate center of mass. We did this in BMD, right, as well, using TK console. And so it tells us the center of mass of all of those atoms is at this location. You could actually go and compare that to BMD if you wanted to see that it's giving you the same answer, to see whether or not you should believe it. We can also calculate the center of geometry. What do you think the answer for this one is going to be? What's the x-coordinate of the center of geometry of the carbon alpha atoms? It's, yeah, basically the same as the last thing. So, so we have center geometry, and then we have total mass. We can add up like that. So, and then you can find a bunch of other commands as well on the MD analysis website. Go ahead and see how we would calculate a distance between two selections. And for those two selections, let's use the center of mass of residues 1 to 5, and then the center of mass of residues 18 to 20. And so those more or less correspond to the N-terminal and C-terminal ends of the trip cage protein. Okay, so one end and the other end, and we're going to calculate the distance between those two pieces of the protein. So how can we do this? Well, actually, one convenient way we can do it is we can set up what's called, and they go through this in the MD analysis website in some detail, what's called a dictionary in MD analysis. And so we can define, so if you just cut and paste this, is probably the easiest way to do this command into your MD analysis your interactive Python session. What I've done is I have defined a dictionary. The first one, so I have this item in the dictionary called nterm. It's a string, and nterm is going to basically be the atom selection, which is protein, and res ID 1 to 5 and name CA. So it's the carbon alpha atoms of residues 1 through 5 of the protein. And then the second item in my dictionary is going to be the C-terminus, C-term I'm going to call it. And that's going to be the atom selection that corresponds to the protein and residues 18 through 20 and the carbon alpha atoms. So it's the carbon alpha atoms of residues 18 through 20 of the protein, which in this case is tripcage. So if I go ahead and take a look at what I've stored into this, so now I've defined this variable called domains. I can do domains items, for example, 0. And what that is that is C term, and it tells me that that has 3 atoms in it. So it's an atom group with 3 atoms at the C terminus, which makes sense because I told it to use amino acids 18 through 20, 18, 19, 20. That's 3 atoms, right? I could also look at 0, 1. That tells me it's the atom group with 3 atoms itself. So domain.items 0 refers to both the C term string name and the atom group. The first element then is going to be this atom group with 3 atoms. And what I could do is I could then calculate the centroid of that, and that would give me the basically centroid position of those 3 atoms. Okay, any questions about that so far? Okay, good. So then I don't want that specifically. What I would actually want, for example, are the x, y, and z coordinates. I can refer to those by adding this extra square bracket 0 at the end. So 0 would be the x coordinate, 1 is the y coordinate, and 2 is the z coordinate of that particular selection. Okay. Any questions about how to use that kind of domains.items? Yeah.
I'm just a little confused. What do the first and second 0, I mean the 0 and 1 in the brackets refer to the n and the c term?
Yeah, so okay, so domains.items, right? So this has both this first library item, which is C term, atom group with 3 atoms, N term, atom group with 5 atoms, right? So now if we look at the 0th element of that, that's going to pick out this first piece, right? This is the 0th element, right? The one after the comma is the first element, right, of that dictionary. So that corresponds to that first thing there, right? So now when I add, for example, if I put in a 0, that's going to be the first element of this variable, right, which is C term. If I put a 1 in there, that's going to be this element, which is the atom group with 3 atoms. Does that make sense? Right, so I'm just basically asking for pieces of the kind of the variable a level higher, if that makes some sense. So,
Well, 1 would be like the second term of the.
Right. If I typed in 2, it would tell me that that doesn't exist. Right. Exactly. Right. Okay. And so now what we can do is we can do a calculation. So we can calculate basically everything. So we want in terms of those distances. So how do we do that? Well, let's go ahead and let's do the center of mass calculation. So we'll skip this centroid calculation for now. So we're just going to define a variable called center of mass. So CM is equal to, now we're going to have our dictionary variable, which is going to look at both name and something that we're going to call DOM.center of mass. And this is basically a iteration. So I'm going to look at all of the names and all of the possible values of DOM in domains.items. So we'll take a look at what this actually means. So if I do that, I type in CM, you see that now the contents of the CM variable, okay, are the center of mass of the C terminus and the N terminus. So what did this do? This looped through, right, basically that variable domains.items, okay, and it calculated the center of mass of the C-terminus, and then it calculated the center of mass of the N-terminus. Okay, so this is a quick way to kind of iterate through a list of items that you want to calculate centers of mass for. You could have as many different regions of the protein as you want selected in that dictionary, and then you can iterate over all of them very quickly, calculate centers of mass of each of them. Okay, any questions about that? Okay, so now let's go ahead and take a look at how we do NumPy subtraction. Okay, and so the first thing we're going to do is we're going to do a little bit of an aside and just make sure that we understand how NumPy subtraction works. So what we can do, let's just define a variable called A1, and let's make it into a NumPy array. So we can do that with np.array, and let's give it the value 0, 0, 0. Okay, so A1 now is just an array 0, 0, 0. A2, okay, let's go ahead and define a NumPy array, which is going to be 1, 0, 0. And then we can use a calculational function in NumPy called norm. We can do norm A2 minus A1. And it's telling me norm is not defined, so maybe it's np dot.
Did you import that language thing?
Import, no, I didn't. Actually, I missed that. Yep. So we need to import from the linear algebra library. Thanks for catching that. So from NumPy, import numpy.linalg, import star. Okay, now if I type norm, I get 1 for the answer. If I, let's say, make A2 equal to np.array instead, so I'm going to redefine A2 as 1, 1, 1, and I use the norm function again, now I get 1.732 blah, blah, blah. So what is this? This is a basically for 3 coordinates, right? This is your distance calculation function, right? This is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, okay? And so we've just done a couple of test cases to just see that this is what this norm function is doing for us when we give it 3 coordinates. Okay, so we believe we understand what the norm function is doing, which is acting as this distance function calculator. So now let's go ahead and use it to calculate the distance in between those selections that we made earlier, the 18 to 20 residue selection and the 1 to 5 residue selection. So how can I do that? What I can do is I can do print. Let me actually just copy this. It'll be a little bit quicker. So what I'm doing is I'm printing, right, the norm of that CM, right? So the center mass function that I define, center mass variable that I find back up here, right? CM had both a C term and an N term, right, item in it, okay? And the second, so basically the second piece of this was the coordinates of the center of mass of the C terminus and the N terminus. So what I'm asking it to do now is I'm asking it to subtract those 2 arrays and then do it in such a way where it's giving me the Euclidean distance in between the center of mass, right? So if I print that, I get 8.26967 blah 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 angstroms for that distance. So what I've done, right? If I typed in C M C term, that's that array, and then CM dot N term, right? That's that array. So I've used the norm function to calculate the distance between those 2 points. Any questions about how to do one way to calculate these distances between coordinates? Okay. So, and then you could go back and you could do this again for the center geometry if you want to do that calculation. And you can also do things like calculate angles and so on and so forth, and those are talked about in the MD analysis tutorial. Okay, so how do we actually do analysis for a trajectory now? Because so far we've been working with just a single frame, really. Well, at the beginning, we loaded in that whole trajectory into our MD analysis universe, right? We said load in prod.1.nc as our file. So first of all, let's go ahead and see how we can figure out the length of the trajectory that we loaded. We can do that in MD analysis using the len command. So len u.trajectory, that's 50, okay? So that makes sense. Each of those pieces of the trajectory that you ran for trip gauge was 50,000 steps. You saved coordinates every 1,000 steps, so you should have 50 frames, okay? So we have 50 frames in that trajectory. What we can do then is we can print quantities over time, and we can do that using for loops, okay? And so here is an example of how to write this for loop in MD analysis. So what we're gonna do is for a time step in u.trajectory, okay? So for a variable ts, what I'm gonna do is try to cut and paste this and see if I can get this to work okay. What I'm gonna ask it to print is basically the frame number and the time, the current time in picoseconds, okay? So I'm gonna ask it to print that, and then I'm gonna ask it to print also the radius of gyration, which you can think about as a measure of the compactness of the protein, basically. And you'll do a little bit with this later on. But I'm gonna ask it to print these two things, so let's hit enter and see what happens. And then you see over that entire trajectory we've loaded, there's a bunch of lines that get printed out. And what the line is the frame number, the time for that particular point in the trajectory. And then the next line, as I asked, was the radius of gyration in angstroms for that selection that I've made, which is u.atoms. Any questions about that? And so you see one of the nice things is in VMD, when I was making these selections, I had to explicitly put in that frame update command to tell it to update the selection every time. MD analysis is doing that internally, so each of these numbers are different. We could, of course, make this output look prettier so that I could print it into an output file and I could graph it. But this is just kind of a quick example of how to get information out of the trajectory frames in MD analysis. So the way you do it is you just loop over some variable for the entire trajectory. Okay, so what if I want to manipulate that data, the radius of gyration data, for example? Well, we can store the data in a variable. How do we do that? Well, we can start by initializing a variable as an empty array. So let's type argir for the radius of gyration and just give it those empty square brackets. And then let's go ahead and make a selection of the entire protein. So we'll use protein is equal to u.selectatoms protein. Okay, I can check that I've actually done that correctly. It has 304 atoms in it. You can go ahead and check in your PDB file, for example, that that's the right number of atoms. So that's 304. And then I'm going to write a loop, which is going to be for this variable in u.trajectory. What I'm going to do is I'm going to append the value of the radius of gyration at each point in time to that array. So I'm going to append at a particular point in time, u.trajectory.time, the radius of gyration of the protein. And so if I hit enter, that'll run, but I don't see anything. But now if I go ahead and type in argir, what I'll see is an array which is going to have the time in one column and then the radius of gyration in the other column. Okay, good. Any questions about that? Okay. And so then if I type in np.array argir, that'll actually turn that into an array, and so I can redefine the variable rg like this. Okay, so now I have this in a NumPy array. Okay, so 2 columns. Let's write it to a data file. So let's see how to do that. So this is kind of the last step. Like, how do you actually get this output to something that's useful to you? And we've done this output in Python before. The first thing that we have to do is we have to open a file that we're going to write to. So we do f is equal to open, and let's call it argir.dat. Let's open it for writing. So this is very similar to what we did in VMD as well, right, in the TK console. Hit enter, okay? And now what we're going to do is we're going to go ahead and create a loop iterate over that variable argir that we made, and it's going to write every line of that argir array to a data file. Okay, so what does this loop look like? Well, this loop looks like the following. The first thing we're doing is we're selecting our iteration variable, let's call it I, and we're going to go from 0, right, which Python starts at the 0 index, up to the length of argir, right? So what is the length of argir? Actually, let's look at that first. So let me delete this. Length of argir is 50. That makes sense, right? I had 50 frames. I have 50 values in there. So let's go ahead and copy this again. So I'm going to loop in that range. And then every time I go through the loop, what am I going to do? Well, I'm going to write to the file. Okay. And what I'm going to write is I'm going to write the basically argir for that particular row, column 0, right? So I0, which is going to be the ith row, right, of the array, the 0th column. And the 0th column, what does the 0th column have in this case? What's stored there? Anybody? The time, right, the time. And then the next thing I'm going to write is the value of radius of gyration, the ith row, the first column. What's stored in the first column? The radius of gyration, right, exactly. And so this is one of the ways you can do this writing syntax. So over here in parentheses, what I have is something that says that this first variable over here after the parentheses, after the percentile sign, is going to be a basically a number that has 5 spaces reserved for it. The second thing is going to be a floating point quantity. It has 8 spaces reserved for it. 3 of those are going to be after the decimal. And so then if I hit enter and I hit enter again, it'll go through that loop. And then I need to close my file. So I do f.close. And now if I type ls, I should see a file in my directory called rgyr.dat. Okay, so that's the radius of gyration. So let's go back over here. Let's go ahead and close this day 8 tutorial file. Let's take a look inside that file. And what do you see? Well, you see 2 columns, right? So the first column is the time values, and the second column is the radius of gyration values. Okay, so in fact, we were able to just print out all that data to the screen. How do we plot it? Okay, so if we actually want to look at a graph of this, well, let's look at this quick plot underscore argir function. This is a Python plotting script. Okay. So in Python, there is this, if you have it installed, which you all hopefully have it installed on your and accessible, you have what's called matplotlib, which is a bunch of plotting library functions which are very useful. This second line here is something that we had to add because if you run this on the cluster, we're not using an X server, basically tunneling over X11, so you're not going to be able to get graphical windows on your local machine over the cluster, from the cluster. So we're going to basically have this line which says don't try to create a pop-up graphical window of the graph. We're instead, at the very bottom, we're going to save the figure as a PDF file and then look at it locally as a PDF file. So what is this plotting file doing? It's importing all the matplotlib stuff that you need. It is loading that rgir.dat file using a numeric Python function called load text. And so it's loading that all into a variable called a. The x values, right? So on our graph, of course, we need something on the x-axis and something on the y-axis if we're making a 2-dimensional graph. The x values are going to be every row. That's what this colon by itself means before the comma. Every row of the first column, right? Those are the times. We want the times on the x-axis. And then the y values are going to be variable a, every row of variable a, the first column, which is the radius of gyration data, right? So I've just stored those two columns from this radius of gyration.dat file back to these variables xvals and yvals. Plot, this is just a standard way to do this. So I have this AX variable, which I define as the subplot region using the plt.subplot function. I'm going to tell it to make a plot where I use the xvals and the yvals. This refers to the style of the line that it's going to use with, and then this is going to be a label for the graph, which just says radius of gyration on it. I'm going to label my x-axis and my y-axis using these set x label and set y label functions. And then finally at the end, I'm going to tell it to save the figure to rgyr.pdf. And then I call the plot plt.draw function to tell it make the figure now. And then you should, if you run this, see your final figure in the directory. So if you go back over to your IPython window and you type in run quick underscore plot underscore rgyr and hit enter, it should complete. You should type ls and you should see a PDF file in your directory. Does everybody see that? So now I want you to download the PDF file. Let's go ahead and take a look at it. So go ahead and download it to your local machine. And then however you open PDF files on your machine, go ahead and do that. And if you plot that, you'll see what the radius of gyration looks like over time. Any questions? Yes, Matthias.
None of the stuff that I was making in the IPython was actually, like, except the origin.dat, like it made a file like that, and when I typed the VI into it, like it was actually, did you close it?
Yeah, did you do the f.close? You have to close the file at the end.
Yeah, I did.
You did?
Mm-hmm. And like I checked like my origin, I had all the positions, like it had the timestamp and like a frame in it, like in the two columns.
Yeah, we'll need to look at it one-on-one. I mean, yeah, I don't know what the problem is,
I
but
realized nothing was saving. Like my select was my select. The reason why I moved it over is because like it didn't save it to my directory.
okay, there's probably some typo or something. We'll take a look and see. But anyway, so that's how you can make a plot of data once you have the data put together. So it is a little bit afternoon. So what else is talked about in here? You can do this on your own, but basically the next little bit talks about some built-in analysis modules that MD Analysis has. And so what you can do is you can import a number of functions from MD Analysis. For example, in BMD, you saw when we wanted to do an RMSD alignment, we opened up that RMSD trajectory tool, we clicked the align button, we clicked the RMSD button, and it gave us both an align trajectory and an RMSD of the trajectory frames with respect to what we aligned it to, which was the initial frame. There are also some built-in analysis functions within MD Analysis, for example, align and RMS, which you can play with here and figure out how to use and what it does, and compare that to what the RMSD tool is doing in BMD. So go ahead and finish going through these last few lines of this tutorial on your own, figuring out how to do this. There are a number of other analysis packages as well, which you can look at on the MD Analysis website. Okay, so what is your project for today then? Finish the MD Analysis tutorial, go through the CPP trash directories and run those analyses on the TripCage system to see how CPP trash works, okay? And then the final part of the project will be to do some stuff with the trajectories you ran yesterday. So let's just go over this briefly. So one thing that I want you to do is to calculate the distance between your sulfur atoms of any pair of the cysteine amino acids that you had in your system. And that's whether you had the disulfide bond or not, because you're going to compare those with your partner from yesterday. Over the entire trajectory, and use both VMD, CPP trash, and MD Analysis to do those distance calculations. So figure out how to get that to work in all three of the programs and compare those distance calculations in each of those. Okay, the second thing, and what I would recommend doing is by the entire trajectory, I mean one of those concatenated trajectories where you splice all of the individual pieces together and filter, let's say, by a step of 10 or something. So you're not doing it for a crazy number of frames. You're just doing it for a handful of frames. Okay, the next thing that you're going to do is do a radius of gyration calculation over time of your protein. I want you to try this with both CPP trash and MD analysis. So we just went over how to do radius of gyration calculations and MD analysis. There's a radius of gyration subdirectory within the CPP trash folder, which will show you how to do it in CPP trash. So after you do it for trip cage, you should be able to apply that to the proteins that you ran yesterday and take a look at those. The next thing you should do is do RMSD calculations. Again, and this describes this in detail, the specific RMSD calculation I want you to do. But again, trying it in VMD, CPP trash, and MD analysis for your protein, seeing that you get similar answers. And then the final bit here is now you're going to try to calculate just an RMSD of a small region of your protein. And what I want you to do here is first align basically to all the alpha carbons in the system, okay? But then calculate the RMSD of just a subregion of the protein. So you do a full alignment of every frame to the initial frame, but then calculate the RMSD for just a small segment of the protein. And for each of you, that small segment, let's just say, let's use residues 1 through 20 in your structure to do the RMSD calculation. But the alignment is for the full system. Do this in VMD and MD analysis and see whether or not your answers agree when you do it. If they don't, then I want you to try to come up with some approach to resolve the conflict about which one of the two tools is actually doing what you what it should be doing, what you expect it to be doing in terms of the calculation. So come up with some way to figure out kind of which one is giving you the answer that you expect. Any questions about any of that? Okay, good. So if there's no questions, I'll be around again for the rest of the day in the office next to Martin's office. So feel free to stop by if you get stuck on anything. For those of you that are still having trouble with getting IPython or MD analysis or whatever to run, so is there anybody that's the case for still? Rebecca, it's not working? The IPython? So we'll take a look at that and try to figure out what's going on there. But yeah, other than that, go ahead and break for lunch and then come back and work on this stuff and ask questions if you have them. All right, great. Thanks, everybody.